శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది. 2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning. Okay, in the last classes we discussed about the filter characteristics, distortion, transmission of linear systems, and energy density spectrum and power density spectrum, right? Okay, now we are going to discuss about the causality and physical realizability, that is also called as the Paley Weiner criteria. What it called? The Paley Weiner criteria, causality and physical realizability. What is meant by physical realizability? Physical realizability of the systems, it is defined like this. So it is defined as physically possible from those that are not. Physical realizability means, physical realizability of the systems means it is defined as physically possible from those that are not. So here we will assume something. From that we will define physically it is possible. Okay, so physical realizability of the systems is defined as physically possible from those that are not. From those that are not, just we are assuming something, and we will define physically possible. Yes, that is called physical realizability of the systems. Physically possible from those that are not. Okay, the physically realizable system cannot have a response before the driving function is applied. So it doesn't have any response before the driving function is applied. Driving function means what is the role of the driving function? It drives something. It drives the system. Okay, the role of the driving function is driving capability of the system. Okay, so physical realizability or physically realizable system cannot have a response before the driving function is applied. So this is called the causality condition. What is meant by physical realizability of the system? It is physically possible from those that are not. Physically possible from those that are not. Okay, physically possible from those that are not. So we are assuming something, and we can say that physically possible from that. And physically realizable system cannot have any response before the driving function is applied. A physically realizable system cannot have a response before the driving function is applied. So this is known as the causality condition. So causality condition may also be expressed alternatively as a unit impulse response. Suppose impulse response, that is h of t. A unit impulse response h of t of a physically realizable system must be causal. So it is the another definition of the causality condition. In another way, the causality condition may be expressed as h of t is equal to 0 for t is less than 0. H of t equal to 0 for t is less than 0. So causality condition may also be expressed alternatively as a unit impulse response h of t of a physically realizable system must be causal. That means h of t is equal to 0 for for t is less than 0. So the above is the time domain criteria of the physical realizability. For frequency domain, the response and sufficient condition is the above one is the condition for causality in time domain, that is h of t equal to 0 for t is less than 0. In frequency domain, it is defined as integral minus infinity to infinity mod natural log of mod of h of j omega by 1 plus omega square into d omega must be less than infinity. It must be some infinite value. Okay. In time domain, it is causality condition is defined as h of t equal to 0 for t is less than 0. And in frequency domain, it is defined as integral minus infinity to infinity mod of natural log of mod of h of j omega by 1 plus omega square into d omega must be less than infinity. It means that it must be a finite value. Okay, it must be a finite value. It should not it should not infinite value. Let it be considered as equation number 1. Okay, let it be considered as equation number 1. Then the magnitude function mod of h of j omega must be square integrable before the Paley Weiner criteria is valid. What is meant by square integrable? It must be integrable and it must be squared. That is integral minus infinity to infinity mod h of j omega whole square d omega. It also must be a finite value. It should not be an infinite value. Okay. So the magnitude function mod of h of j omega must be square integrable before the Paley Weiner criteria is valid. That is integral minus infinity to infinity mod h of j omega whole square d omega must be less than infinity. Here the magnitude function h of j omega may be 0 at some frequencies, but it cannot be 0 over a finite band of frequencies. So it may be 0 at some frequencies, but it cannot be 0 over a finite band. Suppose if you take some finite value, finite range, if you take some finite range, it cannot be 0. Or if you take some infinite range, it may be 0. Okay. So, but it cannot be 0 over a finite band of frequencies, since this will cause the integral in equation number 1 to become infinity. Okay, since it will cause the integral in equation number 1 to become infinity. Thus, mod h of j omega is equal to k into e power minus alpha mod omega is permissible. So the magnitude must be some constant k into e power minus alpha into mod omega. Then only it cannot be 0 over a finite band of frequencies. So that implies mod h of j omega is equal to k into e power minus alpha mod omega place in the place of mod omega we can write omega square is not realizable. Okay, so only k into e power minus alpha into mod omega is permissible. Okay, here what we have to discuss in this causality condition or Paley Weiner criteria. So first of all, we have to define the causality condition. What is causality condition? What is meant by physical realizability and what is meant by causality? Physical realizability of a system is defined as physically possible from those that are not. Okay, physically possible from those that are not. Right? Okay, next coming to the causality condition, the physically realizable system cannot have a response before the driving function is applied. Before the driving function is applied. If you apply the driving function, then only the system will drive. Okay, system can drive. So without applying the driving function, so the physical realizability system cannot have any response. Okay, the physically realizable system cannot have a response before a driving function is applied. So this condition is called causality condition. So it also expressed alternatively as unit impulse function. If you take h of t as unit impulse response, then physically realizable system must be causal. Then we can say that h of t is equal to 0 for t is less than 0 in time domain. In time domain, in when coming to the frequency domain, the necessary and sufficient condition is integral minus infinity to infinity mod of natural log of mod of h of j omega by 1 plus omega square into d omega must be less than infinity. Let it be considered as equation number 1. After that, the magnitude function h of mod h of j omega must be square integrable before the Paley Weiner criteria is valid. When will this Paley Weiner criteria valid? The magnitude function mod h of j omega must be square integrable. It means that integral minus infinity to infinity mod h of j omega whole square d omega must be a finite value, that is it should be less than infinity. Okay, so here the magnitude function h of j omega may be 0 at some frequencies, but here it is not 0 during the finite band of frequencies, since this will cause the integral in equation number 1 to become infinity. So here the magnitude will become h of j omega mod h of j omega equals some constant k into e power minus j into r minus alpha into omega is permissible. Minus alpha into omega square is not permissible, is not realizable. Okay. Let us consider the ideal filter characteristics. Ideal filter characteristics are like this. Ideal filter characteristics are shown as h of it is the graph between h of mod h of j omega versus omega. So here the ideal filter characteristics will be like this. This is the uh, characteristics for limited band of frequencies, particular band of frequencies. Okay, so this is the figure related to physically realizable filter characteristics. Physically realizable filter characteristics. So some particular band of frequencies must be permissible here. Okay, some particular band of frequencies must be permissible here. Okay, so the low pass, this is low pass filter characteristic. So the low pass filter characteristic shown in the above figure is physically realizable for arbitrary small value of epsilon. These characteristics do not violate the Paley-Weiner criteria. These characteristics does not violate the Paley-Weiner criteria. So here is a low pass filter. These are the low pass filter characteristics. So this is physically realizable for arbitrary small value of epsilon. See the arbitrary small value of epsilon is as shown in the figure. See the in the diagram. This is the epsilon value. This is very very small value of the mm, curve, small value of the curve. So it will not violate the Paley-Weiner criteria. So Paley-Weiner criteria means so it is here the magnitude of the given function h of j omega must be equal to some constant k into e power minus alpha into mod omega is permissible. Some constant k into e power minus alpha into mod omega is permissible. Minus alpha into omega square is not permissible. Okay, or is not realizable. Okay, h of j omega versus omega curve must be like this, and there is a small error. This is epsilon is not some error. Okay, mean square error. Okay, so this will not affect or this will not violate the Paley-Weiner criteria. Okay, so the above figure is physically realizable for arbitrary small value of epsilon. These characteristics does not violate the Paley-Weiner criteria. Okay, so this is about the physical realizability or causality and physical realizability are Paley-Weiner criteria. It is very very important question, may ask for 7 marks. Okay, so first of all we have to define the causality condition or physical realizability. What is meant by physical realizability? It is physically possible from those that are not. It is defined like this. Uh, physical realizability of a system is defined as physically possible from those that are not. It means that we are assuming something. Actually, there is no system at there. So, but we are assuming that there is a system at a particular place. Okay. So from that system, we are retrieving something. That means it is defined as the physical realizability of a system is nothing but defined as physically possible from those that are not. Physically possible from those that are not. Okay. Physically possible from those that are not. Right. So after that, we'll see the causality condition. What is causality condition? Before the driving function is applied, the physically realizable system does not have any response. Before the driving function is applied, the physically realizable system cannot have any response. That is called causality condition. Causality condition. Also, it is also uh, it can be also defined alternatively as for time domain h of t equal to 0 for t is less than 0 for a frequency domain it is defined as the integral it must be integrable. So integral minus infinity to infinity mod of natural log of mod h of j omega by 1 plus omega square d omega must be less than infinity. Okay. So before the Paley criteria is valid, so mod of h of j omega, that is magnitude, mod of h of j omega must be square integrable. Must be square integrable. It means that mathematically it is defined as integral minus infinity to infinity mod of h of j omega whole square d omega must be less than infinity. Okay. So here the causality condition satisfies or it must be permissible if and only if mod h of j omega, that is the magnitude of h of j omega, is equal to some constant k into e power minus alpha into mod omega is permissible. After that, we will see the ideal ideal filter characteristics, low pass filter characteristics. These are like this. So here we may get some small error, that is mean square error, that is epsilon. It will not violate the Paley-Weiner criteria. Okay, it must be some negligible amount of value, negligible amount of value. So it is almost all close, very close to the zero, very close to the zero level. Okay, so it is a very small value. So it will not violate the Paley-Weiner criteria. So this is about the causality and physical realizability are Paley-Weiner criteria. Very important. This one is very important. This unit is almost all over. Okay. So what we have discussed in this unit, first of all, we discussed about the linear systems. Okay, how the system is defined, linear system. What is meant by linear system? So these are all the first of all we will discuss about the classification of systems. How the systems were classified: linear systems, non-linear systems, time variant systems, time invariant systems. Right? Linear systems, non-linear. What is meant by linear system? A system is said to be linear system if it obeys the scaling property and superposition theorem. If it obeys the scaling property and superposition theorem, right? So that is the linear. That is the definition of the linear system. Okay, linear system. So which obeys the scaling and superposition. What is meant by scaling property? Scaling property is nothing but if the output is related to input signal or input is related to output signal, vice versa. Here, if we take f of t is the input signal and r of t is the output signal. If f of t is related to r of t, or r of t is related to f of t. Similarly, some constant into input signal f of t is related to some constant into output signal r of t. Okay, so that is called the scaling property. And coming to the superposition theorem, if f1 of t is the input of first system and r1 of t is the the output of the first system. Similarly, f2 of t is the input of the first system, second system, and f R2 of t is the output of the second system. Then the combination of the inputs of first system and second system, that is f1 of t plus f2 of t, combinedly related to the combination of the response of the first system's output and second system's output, that is r1 of t plus r2 of t. Okay, now r1 of t plus r2 of t. Okay, so that is f1 of t plus f2 of t is related to r1 of t plus r2 of t. That is called the superposition property. So on the whole, a system is said to be on the whole, combining the above two properties, that gives the linearity property, that is alpha into f1 of t plus beta into f2 of t is related to alpha into r1 of t plus beta into r2 of t. This is about the linear system. What is meant by nonlinear system? How the system is said to be nonlinear? If the system is said to be nonlinear if it does not obey the scaling and superposition theorems, then it is called a nonlinear system. Then coming to the time invariant system, time invariant system. So, what is meant by time invariant system? With respect to time, with respect to time, the system parameters will not change. Okay, that is a time invariant. The system whose parameters do not change with time is called a time invariant system. If f of t is input signal, r of t is output signal, so f of t is related to r of t, then some some shift in the time, that is tau units, f of t minus tau will relate to r of t minus 2. Here input time is shifted automatically, output time is also shifted. The system which is linear and time invariant, both properties here. So the system which is linear and time invariant, that is called linear time invariant system, which obeys the linearity property as well as the time invariant property, then it is called linear time invariant system, LTI system. Okay, linearity system also defined as there is a linearity between the input and output signals. If we change the input signal, automatically output signal will also change. Okay, so that is also in another way of defining the linearity system like that also. Okay, next properties of LTI systems. What are the properties? Cumulative property, distributive property, associative property, static and dynamic property. What is meant by cumulative property? Here the system having the impulse response h of t is like this, which is having the input signal f of t and the output signal r of t like this. It is described like this. See here the output or response r of t is defined as the input signal f of t convolved with the impulse response h of t, or we can define in another way as the impulse response h of t convolved with the input signal f of t. Here the star indicates star, the symbol star indicates the convolution symbol. Okay, convolution symbol. Next, distributive property. So if the system is having the combination of the impulse response h1 of t and h2 of t like this, and which is having the input f of t and the response r of t is like this, then the response r1 of t is defined as f of t convolved with the h1 of t, and r2 of t is defined as f of t convolved with the h2 of t. Then the combination of r1 of t and r2 of t is equal to f of t converted with h1 of t plus f of t converted with h2 of t. Taking f of t as common, so f of t convolution with or converted with the whole combination of h1 of t and h2 of t. That is called distributive property. Distributive property. And third one is associative property. Associative property. How it is expressed? If R1 of t is the response of the first system, that is R1 of t is defined as f of t converted with h1 of t converted with h2 of t whole, h1 of t converted with h2 of t whole converted with f of t. Similarly, r2 of t is the response of second system, that is r2 of t equal to f of t converted with h1 of t whole converted with h2 of t. Similarly, R3 of t is the response of third system, that is F1 f of t converted with H2 of t whole converted with H1 of t. This is called associative property, right? Uh, Distributive property, associative property, and cumulative property, and last one is static and dynamic property. We already know about the static systems and dynamic systems. Static systems are memoryless systems. They didn't have any memory. Okay, they don't have any storage device. Okay, so static systems are memoryless systems. Okay, they can take mm, input and give output. Okay, and they didn't have any memory. Okay, output depends only on the present input. Okay, in this system, so impulse response, that is h of t is zero. Step for static systems, the impulse response h of t is zero for t is less than or equal to zero. For dynamic systems are one whose output depends on the present and past inputs. So present and past input. Suppose x of t is the present input. Past input means x of t plus 1. Okay, past input. So like that. So we can define y, the response y of t as x of t plus x of t plus 1. So that is the example for dynamic systems. For static systems, example is y of t equal to x of t, or f of t equal to or p of t equal to q of t, like that. Okay, it depends upon the present state of the system for static systems. For dynamic systems, the output depends upon the present as well as past inputs. Okay, next one is the transfer function or system function. Transfer function or system function, both are same. Transfer function is nothing but it is nothing but the ratio of output to the input. Output by input is nothing but the transfer function of the system. It is also called as output by input. It is also called as system function also. So here we are that is the basic definition. But here the response y of t is defined as x of t converted with h of t. But here we are taking the x of t as some exponential function, the input signal as exponential function, that is e power j omega t, e power j omega t. Okay, h of t is the impulse response. Then y of t can be expressed as a convolution formula, that is integral minus infinity to infinity h of t into x of t minus tau d tau. Okay, that is minus infinity to infinity h of t into e power j omega t minus tau. Here h of t into x of t minus tau d tau, that is the definition of the convolution. Definition of the convolution, x of t converted with h of t is defined as integral minus infinity to infinity h of t into x of t minus tau d tau, x of t minus tau d tau. So here the x of t minus tau, so t is replaced by t minus tau, so j omega t is also replaced by j omega t minus tau. Okay, so integral minus infinity to infinity h of t into e power j omega t minus tau d tau. Okay, expand it, e power j omega t into e power minus j omega tau. So extract the e power j omega term outside. So e power j omega t into integral minus infinity to infinity h of t into e power minus j omega tau d tau, or integral minus infinity to infinity h of t into e power minus j omega tau d tau is nothing but h of omega. So it is e power j omega t is x of t into h of omega, right? So where h of omega is this one, or from this we can derive the h of t as 1 by 2 pi integral minus infinity to infinity h of omega into e power j omega tau d tau. So here h of omega is called the transfer function. Okay, so h of omega is given by y of t by x of t at x of t equal to e power j omega t. If we express the input terms in of its Fourier transform, so then x of t becomes 1 by 2 pi integral minus infinity to infinity x of omega into e power j omega t d omega. So substitute this value in equation number 1. We get y of t equal to 1 by 2 pi integral minus infinity infinity x of omega e power j omega t d omega into h of omega. Or we can write x of omega into h of omega as y of omega, or h of omega equal to y of omega by x of omega. That is the system function or transfer function. Next, next we will see the impulse response. Impulse response. So let us consider a system having the input signal x of n and output signal y of n. So the response of the above system y of n is nothing but transformation of the input signal x of n. So here x of n is considered as a unit impulse function. So that is delta n. So it is nothing but transformation of delta n. So the response of y of n is impulse response. So input signal x of n can be represented in terms of weighing pulses or weighted pulses. Okay, that is y of n is a transformation of x of n. So it can be represented as a sigma k equal to minus infinity to infinity x of k into delta of n minus k. Okay, so sigma k equal to minus infinity to infinity x of k into transformation of delta of n minus k. Or we can write this as sigma k equal to minus infinity to infinity x of k into h of n comma k or n minus k. So it is sigma k equal to minus infinity to infinity x of k into h of n minus k. Or finally y of n becomes x of n convoluted with h of n. So after that we will solve some, we'll solve some problems. Okay, and then we discussed about the uh, frequency response. No. Filter characteristics. Filter characteristics. Next, distortionless transmission of a system. Okay, filter characteristics. So based on the filter characteristics, based on the characteristics of the filter, if it is a low pass filter, it allows the lower frequencies. If it is a high pass filter, it allows only higher frequencies. If it is a band pass filter, it allows only particular band of frequencies. So based on the frequency range, based on the characteristics of the filter, it allows the particular range of frequencies. So based on the filter characteristics, it passed the particular band of frequencies. Okay, remaining frequencies are attenuated. It is attenuated, it will be stopped. Okay, so remaining frequencies must be stopped or attenuated. Next, distortionless transmission. Distortionless transmission means if you pass the sinusoidal signal as the input for the system, we will get the same sinusoidal signal as the output of the system. Its amplitude or time delay. These waveforms may have some amplitude variation or some time delay properties. Okay, but the shape of the waveform is same. It is exact replica of the input signal. Then only we can say that it is the transmission, distortionless transmission through a system. Okay, so here the magnitude and phase angles will be defined like this. Here the magnitude mod h of j omega equal to k into e power minus j omega t naught, and phase angle is theta of omega equal to n pi minus omega t naught. Okay, next we discussed about the bandwidth of a system. What is meant by bandwidth? If we take the frequency response of a system, frequency response is drawn between uh, transfer transfer function with transfer functions gain with the frequency. Okay, so from the maximum gain of the system, we will draw the 3 dB gain, that is 1 by root 2 times of its maximum gain. So that the 3 dB line will cut the response at two places. So that particular two places are called lower cutoff frequency. Or here omega 1 is lower cutoff frequency and omega 2 is upper cutoff frequency. The difference of these two is called the bandwidth of a system. Omega 2 minus omega, or we can say that f2 minus f1. How can we say that it is f2 minus f1? Omega 2 is nothing but 2 pi f2. Omega 1 is nothing but 2 pi f1. 2 pi is common, extract it outside. So f2 minus f1 is nothing but the bandwidth of a system. In some textbooks, it will be represented as FL and FH. FL is lower cutoff frequency. FH is higher cutoff frequency. So the difference of these two is nothing but bandwidth of a system. Okay. Next, energy density spectrum and power density spectrum. Energy density spectrum. How the energy is calculated? Energy is calculated for non-periodic signals. Is it not? Energy signals, non-periodic signals are called energy signals. So it is minus infinity to infinity. Okay, x square of t dt, right? That is the energy signal. Integral minus infinity infinity x square of t dt. Okay, so for non-periodic signals only energy is calculated. So after that, by taking Fourier transforms and something, so finally the energy of a signal E can be uh, expressed as integral minus infinity infinity mod x of omega square df. Similarly, the power spectral density, that is power density spectrum. So for periodic signals, we can calculate the power. So power is calculated for periodic signals. So it is defined as integral minus infinity infinity mod x of t square dt. That is power, or it is also called as mean square value of x of t. That is x square of t bar. Okay, x square of t bar. Or we can also define like this as limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2 mod x of t whole square dt. This is the power density spectrum. Okay, next already we discussed about the causality and physical realizability. This is also called as Paley Weiner criteria. So Paley Weiner criteria, first of all, physical realizability is defined. So it is physically possible from those that are not, and after that the causality condition will be defined. So after applying the driving function only, this will give some response. Okay, realizable system, physical realizable system will give some response after the driving function is applied. Okay, so this is called causality condition. Another way of expressing the causality condition is for time domain h of t equal to 0 for t is less than 0, and for frequency domain integral minus infinity infinity mod of natural log of mod of h of j omega by 1 plus omega square into d omega must be integrable. So here it must be square and integrable. The magnitude function mod h of j omega must be square and integrable before the Paley Weiner criteria is valid. That is integral minus infinity infinity mod h of j omega square d omega must be less than infinity. Okay, so finally the causality Paley Weiner criteria is valid if the magnitude mod h of j omega must be equal to some constant k into e power minus alpha into omega is permissible. Okay, here we are taking the ideal realizable characteristics. Okay, physical realizable characteristics are ideal low pass filter characteristics. These are like this, and these characteristics may have some small error, and that is almost negligible amount of error, which is represented by, which is denoted by epsilon. Epsilon would mean square error. It will not violate the Paley-Weiner criteria. This is about the causality and physical realizability or Paley-Weiner criteria. With this, this unit is also completed. Okay. From next class onwards, we will revise these three units. Okay. With this, I will conclude this today's session. Thank you, one and all.